Hello, this is Roger Tipton from the University of South Florida, and I'm going to be speaking today about an additive manufacturing process for producing integrated flexible optoelectronic devices. As we all know, flexible electronics are a really exciting topic right now, and it's really driving a wearables revolution. I mean, flexible electronics really started as, you'd have a couple boards and you would have them joined together with a flex tail. And then that progressed to, you would have flexible substrates and you would attach components to them and make flexible devices. And then we had the Fitbit came out, and where you really created a commercial product that sensed things like steps and sleeping and said, hey, we can monitor our daily lives and how we are. And Apple really took that to the next level with the iWatch and said, well, we can just put a computer on your arm. And how exciting is that going to be? You can talk on the phone, you can listen to radio, you could, the latest generation, you can now monitor your heart rate and your oxygen levels. It's becoming not just a computer, but a sensor and a wearable and just a multifunctional tool. And really what we're seeing is kind of the next generation will be flexible wearables that will get attached to your skin or implanted or robot skin. I mean, there's all kinds of things we can do exciting with flexible electronics. And another maybe subsection of this field is flexible optoelectronics. And I think we understand the benefits of optical communication. You get higher bandwidth, so you can get more communication down an optical pipeline than you can an electrical one. You have lower power requirements. Copper and things like that heat up. And they're putting data centers in the Arctic now because there's so much heat generated and there's so much power required to cool these things that it's just crazy. And so optics is just an exciting bit of field. And much like flexible electronics, flexible optoelectronics is really kind of started out with, let's just put some LEDs on a flexible substrate. Let's put some rigid components on a flexible substrate. And then, these Android phones have now come out where you have flexible screens where you actually can fold thousands of times and open them and it looks like a single screen. So, optoelectronics, flexible optoelectronics are coming into their own now. And one of the things our research group is doing is we look at additive manufacturing. It is such an exciting new field where you can just produce one of something, or you can fabricate from a CAD drawing. It's just another exciting new to solve problems. And if we look at flexible optoelectronics, the majority of tools used to make these devices are printing methods. So whether it's older school flexographic or gravure printing, where you're rolling on sheets and they roll through a printing press and are rolled up at the end, or they are inkjet printing. We kind of said, well, what could we do with additive and subtractive manufacturing tools to create a better manufacturing process for flexible optoelectronics? And we happen to have done some work in our group and others at the University of South Florida on laser enhanced direct print additive manufacturing. And this is a shape deposition methodology where we use additive and subtractive tools to make a process. So if we were to make a flexible optoelectronic device, let's say something like an optical interconnect, And what we would do first is we would print a cladding material, a liquid urethane on a flexible substrate. And then we would cure that cladding material, and then we'd apply some ABS adhesive with a micro dispenser. And then we would come through with an FDM printer and print the core material, an optical core to go inside the cladding. Then we would finish, cure, and then we would come back and use a laser with a laser ablation process to prepare in facets and cut away extra material. So it's an interesting process. And we happen to have one of these machines at the University of South Florida. It's from Inscript. It's a 3DN machine. And you can see in the first image, we have micro dispensing of the urethane actually on a piece of Kapton. And then we have the FDM printing head, printing the core. And this is a laser ablation tooling, and then a finished optical fiber interconnect, ready to be pulled out and used. So how would we make this optical interconnect? What would it look like as an idea and as a finished product? So we have a little cartoon here that describes the cladding. We've got our flexible optical interconnect on top of it with the urethane cladding, the PMMA core, and it's processed using our process. And then afterwards, LEDs, photo detectors, components can get added to this to make a complete assembly. And so what we see in the bottom left here is actual SEM image of a optical fiber interconnect. And you can see the fiber running from the bottom of the page to the top of the page, and it's on a flexible substrate. And then we came through and embedded the fiber in the cladding, and then we've used laser ablation to cut the fiber and expose the in facets. And then what we would do is remove the rest of the top half of this image, and then we would have an optical interconnect ready to be used. On the right, we've added some illustrations here to show you kind of where things transition. But you can see there's a 50 micron Kapton substrate, there's the cladding material, and then you have a core of PMMA running along this way, and then a circular in facet that can be connected to either source or detector. So these are actual fibers that were made in our lab. And one of the things when you make a flexible device for optoelectronics, some of the things that you worry about is how will this perform in bending tests. And so what we did is we did some numerical simulation where we actually created a fiber on a substrate with cladding material, and we bent the assembly in the simulation. And we used two different sizes, 150 micron substrate and a 50 micron substrate. And we saw in the 150 micron, as we bent from 30 to 280 degrees, we saw strains go up to 0.5 millimeter per millimeter. And obviously, the 50 micron substrate, we had less strain in the entire assembly, and it was about 0.1. So we felt that 50 micron substrate was probably the optimum choice for our work. And we also see that with the warpage. We're putting a hot fiber on a flexible substrate, and so warp was a concern. And then we see, from 125 micron down to 50 micron, we were seeing less than 1 micron of warp. So it really wasn't a big concern in our product. And then we said, well, we're making this flexible optical interconnect. What will be the performance of this product as it's bent optically? And in this particular case, we chose a high delta N between the core and the cladding to improve optical bend performance, and all the way down to 1 millimeter radius before we started to see a breakdown of loss. So we thought this is going to be an excellent product for bin simulation. And we've actually made hundreds of fibers, and we put them through some of the standard tests for transmission insertion loss, and then calculated the propagation loss. We're less than 3.5 dB per centimeter, which we thought was very excellent, 0.35 dB per centimeter. And we change in insertion loss as we bent the fiber, so it was very consistent in the theoretical is the blue line. So it was very flat at less than 0.5 dB per centimeter. And then it really increased dramatically as we got around 6 millimeters in bend radius, which is somewhat similar to the theoretical values we had calculated earlier. And as far as the change in insertion loss, as we flexed this over and over, looking for problems with fatigue at 1,000 cycles, we hadn't seen any issues yet. So as far as making samples and testing samples and results, it's been very exciting. So what have we learned through this? And what we did is we proposed that we could make flexible optoelectronic devices using this LED PAM methodology, where we would use additives and subtractive tools to fabricate the fiber instead of the traditional contact and non-contact printing tools that are used with most projects. And we were actually very successful in this, and we've demonstrated that through processing and through simulation that we can create a fiber. And we think that, finally, we think that we can use these tools, these additive manufacturing tools, to create a whole range of flexible optoelectronic devices. We think additive manufacturing is created a whole range of products that can be made. So we feel this is an exciting new process, and we've just at the beginning of what we can do with it. So I would like to thank our team, our research team, and I'd also like to thank the NREC, which is a facility at University of South Florida. It's our nano materials lab for SCM equipment and support in some of these studies. And I'd also like to thank our funding sources, Path Optical Systems, the Bragg grant we received, the CADE prize that we won for some of this research, the support of NASA and I-Corps in helping us fund this project. So I'd like to thank everyone, and goodbye.